All right, chemistry. So we're going over, it's called the combined gas law. Now the combined gas law really only ties in 3 of the 4 variables. So if you remember, we've got our 4 variables. We have pressure, we have volume, we have temperature, and we have amount. So really, the combined gas law doesn't include the amount. So it's really only good for situations in which the actual amount of gas is fixed. So amount must remain constant. So that means no gas going in or out of the container. So it's a fixed amount. Now what we tend to do is we look at it in terms of a change that's going to happen. So we have like the situation before and a situation after. So our formula comes out looking like this. P1 V1 over T1 equals P2 V2 over T2, where the 1 represents either the starting or it could be just a situation, and the 2 represents the new situation that we're going to go through. Now if you notice, this is an issue that we see with the combined gas law, is that temperature shows up on the bottom, and because we have temperature on the bottom, it means that we have to use the Kelvin scale. Now, the reason why it has to be the Kelvin scale is because it's the absolute scale, and it starts at 0. So in other words, we don't have to worry about having a 0 on the bottom of the denominator, because that would cause a problem. And the other thing that we know is that there's no negatives. So having no negatives means that we're going to be fine. We'll never end up getting a negative volume out of this problem or a negative pressure, and that wouldn't make sense in the real world anyways. So that's why we always have to make sure we're using the Kelvin scale. Now if you remember from our green sheet, hold on one second. From our green sheet, we have a way to kind of show the Kelvin scale and how the Kelvin scale fits in. It's really that whatever your Celsius degrees are plus 273. So we're just adding 273 to that. Now we don't always use the combined gas laws with all 3 variables. Sometimes we're going to maybe have a constant in here. So like, let's say that the temperature is going to remain constant. If that's the case, then we cover up the temperatures and we see that P1 V1 equals P2 V2. If the pressure were constant, then we would cover up our P's, and we would have then V1 over T1 equals V2 over T2. And if the volume was constant, then we would get P1 over T1 equals P2 over T2. So again, the relationships, if you remember from yesterday, the indirect relationship is this one, so that's the indirect relationship. The direct relationship is this one and this one. So we can kind of see how those are set up. Let's go through a couple of sample problems. That'll kind of help us get a better understanding. Okay, and so I'm going to start with this as a sample problem. So I've got a sample of helium gas, has a volume of our 200 milliliters at 0.960 atms, and we want to know what is the pressure if we're going to reduce the volume with having some constant temperature. So again, we do recognize that this is going to be constant temperature, so really it's P1 V1 equals P2 V2. And then what I like to do is I like to list out all of our variables. So we've got a P1, we've got a V1, we've got a P2, and we've got a V2. And so I look at the problem and I say, which pressure and volume go together? So we've got a sample volume of 200 milliliters. So I'm going to put 200 milliliters. Pressure, oh, I wrote that wrong spot. So 200 milliliters. Our pressure was 0.960 atms. So those two go together. They're looking for a new pressure, so I'm going to put a question mark there, and they want that in atms. If we have our volume, need to reduce the volume at a constant temperature to 50 milliliters. Now, here's one of the things that we always want to watch. We want to make sure that the units match. So this is a volume unit in milliliters and a pressure unit in atms. So we're good to go here with our units. We don't have to do any unit conversions. Now what we're going to do is we'll set this up. So our pressure is going to be 0.960 atms. Our volume is 200 milliliters. Our new pressure is our question mark. And our new volume is 50 milliliters. Okay? And then it just becomes an algebra problem. So all we have to do now is solve. So we'll divide by our 50 milliliters. And our milliliters will cancel out and we'll get our answers. Then we just have to grab our calculator. Grab the calculator here. And we'll walk through. Punch in our numbers. Okay, so we got 0.960 times 200 divided by 50 comes out to be 3.84 atms. Let's just double check. I've got 1, 2, 3, 3, 4. So 3 significant figures. So there's our pressure. Okay. Let's try another example problem. Okay. I'm going to take this. Let's get rid of this one. Here's our next one. We've got a certain quantity of a gas that has a volume and a temperature. And we want to know what temperature in degrees Celsius would this quantity of gas be reduced to, assuming constant pressure. So again, we know that it's going to be under constant pressure. So that means that it should be V1 over T1 equals V2 over T2 because the pressure is constant. So I just removed the pressure. Now we're going to list our variables out. So V1, T1, V2, T2. And we're going to find the ones that kind of go together. So V1, that's our volume, 0.750 liters at 298 Kelvin. That's good that it's in Kelvin because we need that to be that unit type. Then they want to know what temperature, but they want that in degrees Celsius. And we know that it's going to be 0.500 liters that we're reducing it to. So I've got my values set up. I know what equation I'm going to use. Now I'm just going to set this thing up and solve it. So I'm going to put my 0.750 liters over my 298 Kelvin equals 0.500 liters over T2. Now this is the trickier algebra problem. Okay, so I like to kind of talk about this when that variable's in the bottom. We're going to bring that variable up here. Okay, and then we're kind of doing a little cross multiply. So this one's going to go back up over here, and this one's going to go back down here. So I'm going to rewrite it just showing what we just did with our algebra. So it's T2 equals 0.500 liters times 298 Kelvin divided by 0.750 liters. So really we kind of flipped. This went down, this went up, and then this one is where our variable comes over. Now we can just go through and do our calculator work. Okay, so we're going to clear that. Do 0.5 times 298 divided by 0.75. looks like we get an answer of 198. Let's see, 1, 2, 3, 1, 2, 3. I'm going to wait 199. This is Kelvin. Now, they wanted this in degrees Celsius. So again, if we go back to our formula sheet, the Kelvin temperature is equal to the Celsius temperature plus 273. So really all we have to do is subtract 273 from this to get our Celsius temperature. So minus 273 comes out to be a negative 74 degrees 0.3 degrees, actually should just be a negative 74 degrees Celsius if I'm following my significant figures, because again I'm just watching the place value, so negative 74 degrees Celsius. And then I've got one more example problem we'll walk through. So let's go ahead and we'll take one more example. Okay, so here we go. We've got an aerosol can that contains gas under a pressure, so we know that it's under that pressure at that temperature, and they want to know if the can's left out on a hot day, the pressure of the gas increases to this. What is the Celsius temperature on the beach? So again, we're going to just, let's see, are we pressure and temperature? Oh, it looks like our volume, because the can is a fixed thing, so this is a fixed volume, so volume is constant. Okay, so if that's a constant, then we're going to get rid of that. We're going to get our P1 over T1 equals P2 over T2. And so then we can go through and set this one up. And so again, I'm going to do my P1, T1, P2, T2, list out my variables. So I have 4.50 ATMs, 20 degrees Celsius, and I got 4.80 ATMs, and they want to know what's that in degrees Celsius. Now this is the one that catches most people, because the temperatures are in degrees Celsius and they forget that we have to be in kelvins. So remember that we have to go through and make a Kelvin change here. So I'm going to do 273 plus my 20 comes out to be 293 Kelvin. So this temperature, okay, that T1 is going to be that. So now we can set this up. 4.50 ATMs over 293 Kelvin equals 4.80 ATMs over T2. Now we just have to go through and do that same algebra step that we did before. So remember that this temperature is going to go up, this pressure is going to go down, and this temperature is going to go up. So I'll rewrite it so I don't get it wrong here. T2 equals 4.80 ATMs times 293 Kelvin divided by my 4.50 ATMs. ATMs cancel. We're going to get an answer in our degrees Kelvin. So let's go ahead and do that. So 4.8 times 293 divided by 4.5 comes out to be 312, okay, 313 Kelvin. So now we have to subtract our 273 because they wanted the answer in Celsius, so minus 273 comes out to be 40 degrees Celsius. Okay, and so that's our three examples. Now, in the three examples that I showed, nowhere did we use all three variables at the same time, but we could have. So you just got to be aware, we could use all three variables. One more thing I should probably bring up would be, let me see if it's we didn't talk about standard temperature and pressure. So let's go ahead and talk a little bit about that. This is called STP. It's the standard temperature and pressure. And what we do is we tend to standardize gases. So standard temperature is always going to be 0 degrees Celsius. That's the same as 273 Kelvin. And the standard pressure is always 1 atm. And I think this is on your green sheet. I dropped it here a second. Grab it. And let's double check here. So you should have something like standard temperature, standard conditions, 1 atm, and 0 degrees Celsius. So sometimes we're just converting using the combined gas law to convert something into standard conditions, and there's your two values for your standard conditions. All right, if you do have questions, just ask in class and have fun with your combined gas law.